Yeah, very good evening to each and everyone who have gathered today through online and also through Facebook Live for our SSC e-talk series. This is the 8th e-talk of the series. So far, we have completed successfully 7 e-talks in the month of May and June, and we also have few more talks lined up in the month of July. I am Dr. A. Deepak, Associate Dean International Affairs, Saveetha School of Engineering. I'd like to thank our director, madam, for madam's kind support and guidance, initiation in organizing this event. Then I will also extend my thanks to our principal sir for his continuous guidance. I would also like to thank our vice principal sir for his support. Today we have with us Dr. Bogdan Gita from the University of Plymouth, UK. He is currently working as associate professor in the School of Engineering, Computing and Mathematics. His current role includes he is the leader of network research within the Center for Security, Communications and Network Research. He is the coordinator of international activities for School of Computing and Mathematics. He has completed his PhD in the year 2004 in the topic Performance Characteristics of IP Networks. He has professional membership in MBCS, Member of British Computer Society, since 2005. He also acted as external member as a reviewer for UK-India Education and Research Corporation, external examiner for computer networks at Northeast Wales Institute of Higher Education, then external examiner at University of Berkshire. His area of research includes computer networks, wireless networks, and networks performance. His research interest includes performance measurement and evaluation for IP networks, performance modeling for TCP-based applications, network security. Under his guidance, around 6 people have completed a doctorate. He also received a grant of more than £1 lakh for his research work. He has published more than 100 papers in research journals and also conference proceedings together. He has addressed in various forums. I'm very happy to welcome Dr. Bogdan Gita, Associate Professor from University of Plymouth, to address the gathering. Over to you, Professor.
Many thanks, Deepak. Thank you very much. And I'd like to welcome the audience. I can see 31 participants on Zoom. I imagine there are a few others also joining us via Facebook. Just to clarify, yes, Gita is my surname. I'm very well aware that is a female name in India, and I've been at the airport quite a few times being told, no, you cannot take this taxi because I'm expecting a woman to turn up. So I'm sorry, but this is my name. I can't help with that. So my first name is Bogdan. So let's have a chat about the Internet of Profiling, traffic, users, and applications. This is a research that I've done with a few of my PhD students. Some of it finished, some of it is still ongoing. But I think it's a very interesting area of research. Of course, it's my research, so I would say that, wouldn't I? So let's start with a brief outline. I'll discuss about the context. Then we'll move on to the why, the what, and the how of it. So basically, what brought us to this? What is the context? Why did we decide to do this research? What did we actually do? How did we do it? A bit of discussion, and I've got 2 bullet points missing there. A bit of discussion about the results, and also, as you do it in all the papers, some future work. I can see there is a raised hand. Is there a problem? Can you hear me okay? Can you see me okay? Can you see the presentation okay?
Yes.
Okay, right. Thank you. Okay, so let's start with the context. So Cisco are very good at presenting statistics, and 1 or 2 years ago they mentioned that by 2021 we'll have 3.3 zettabytes, so that's 10 to the 21 equivalent to about 278 exabytes per month. Live video will see a 15 times fold increase from 2016. Video will occupy 83% of the bandwidth that we'll be using by 2021, and we'll have quite a bit of content delivery networks that will help with it. So 71% of the traffic is likely to be CDNs. Also, in terms of the players, so these are the predictions. Now, what's happening at the moment? Well, any ISP will say, well, if you have a problem, if your application is slow, or if you have any issues, more bandwidth is better. Have more bandwidth and it will solve your problems. And of course, it will solve definitely their problems, because the more bandwidth they sell, the better they do, basically, financially. Consumer agree with this. So quite a few of the consumers say, oh yeah, more bandwidth is better indeed, but they're going to use it. So if we look now at video, so something that was used for let's say 3 to 5 years ago, that was quite high bandwidth. So say anything above 10, 20 megabits per second, it would be used sporadically, mainly for web pages. Very little of it would be multimedia. Now they're using it. There have been plenty of discussions of whether it's used legitimately or not, because quite a bit of the activity, go back, let's say 10 years or 5 years, was to do with peer-to-peer networking. Now, even that is not the case. So we're seeing now a lot of video traffic, which is legitimate video, is not about copyrighted downloads or anything like that. So it's actually legitimate traffic filling up the internet. So once the consumer said, yeah, bring me more bandwidth, but I will use it, all of a sudden the ISP said, well, CDN, SDN, can you help, please? So I'll expand a bit, just for those of you. I imagine that I've got people in the audience that aren't necessarily with a full networking background. So CDN is content delivery networks, and SDN is software-defined networking. So they need a bit of help, ISPs. So the research jumped in as well, talking about new things. So talking about quality of experience. So up to 5-10 years ago, the quality of service meant delay, jitter, packet loss. So how slow or how fast the network is. I'm not saying that is irrelevant now, but more interesting, the research wants to go all the way to figuring out whether the user is happy. Of course, the user is never happy. That's the definition of a user. The user could be at best indifferent. They will never be happy. And I speak this personally from my experience in interacting with users as well, and being a user. Security as well is an issue. It's an increasing issue because the networks are coming under attack from a security perspective. And of course, software-defined networking is the new kid in town for a few years now and trying to make its way through. But also we can talk a little bit about profiling, and this is where we come in from, because a lot of the research actually tries to figure out, oh, what are these users doing? I can't just give pipes to the users and just assume, well, that's it. I don't care what's going on. A user that will do a lot of, let's say, bulk downloading will be less concerned about the jitter, the delay, the packet loss. Things will just happen in the background. A user that is doing multimedia, a lot of real-time or almost real-time interaction, will say, no, I don't need 1 gigabit per second, but I need delay below 100 or 200 milliseconds. I need packet loss below 1%, and so on. So there are a number of caveats there. There are a number of challenges. And this is why profiling is necessary, because we need to know what users are doing, not in a big brother way, just in terms of, well, some users are doing gaming, some users are doing downloads, some users are just browsing the web, so that we can cater for them accordingly. Okay, so as I said, we need to know what the users are doing, not for big brother reasons. There's a lot of concern about the big state and the monitoring and so on. That is, at least in terms of my research and our research in the group, is not our interest. What we want to know is what the users are doing, so we can provide them with a better service. Essentially, when you look at traffic, well, everything is encrypted. So if you see high levels of traffic, the expert opinion, it must be a lot of video in there because it's a high level of traffic. I don't know what it is. I can't look at it. It's all traffic. It's all port 443 HTTPS, probably video. We can have layer 2 profiles put in place per customers, but we need to make a number of assumptions. So layer 2 profiles means when I'm actually looking individually at each, let's say in the example of a ISP, individual broadband customers. So first of all, assumptions. Probably a user will not do several activities at the same time, because if they do, I can't figure out which is which. I see lots of things in there, but I'm assuming the user is just doing one thing. But actually the user might be, as I've seen plenty of examples, listening to music while playing a game, while running some things in the background, while downloading a movie. Also, probably there will be sufficient bandwidth. So the assumption is that, well, I'm hoping that I will have enough bandwidth as an ISP to actually do this, to provide the customer with what they need. And probably there will be sufficient variation for contention to work. And again, don't want to spend too much time on this, but contention is a big challenge in the sense that the only way for ISPs to work is to resell the same byte to several people. And the typical contention rates, at least in the UK, are somewhere between 1 to 20 and to 1 to 50. So if all the 50 users decide to turn on the internet and download at full speed at the same time, they won't be getting much bandwidth. Also, because the recent years keep telling us that SDN, the software-defined networking, is the answer. So end-to-end provision is expensive to provide and to charge and to bill. We cannot do, so there's been so many discussions about either integrated services or differentiated services. One way or another, you would need to have a full communication end-to-end, so that if me, a user in, let's say, UK, is trying to access a resource on a server in India, then I would need to get all the ISPs along the path to agree, oh yeah, this user needs a very special bandwidth and needs to be provided with that. It's too expensive. And I can't sort of, well, out of the 2.5 pence that I'll be paying for this, 0.02 pence will go to ISP A and 0.05 pence will go to ISP B. It doesn't work. So we cannot do end-to-end provision, but we can accommodate traffic needs at each level. So we can look at access, at aggregation, if possible at core, transparency, in absence of traffic flow or metadata. We cannot sort of, oh, what's this flow? And what are you doing? And what are you doing? We need to do that analysis somehow as fast as possible. And the word fast will come up several times today. And try to figure out what the users are doing, try to have best guesses and try to accommodate them accordingly. Okay, so what do we do? Well, we've got traffic profiling already in place, but at a crude level. So if we start with traffic volume, we've got time bins there. So how much traffic per hour typically, or per peak versus non-peak time, off-peak. That's mostly for present and future capacity requirements. So it's not going to say all of a sudden, oh, I think there's a peak coming, increase the capacity in the next hour. No, that's not going to happen. But if I see my network utilization slowly going up, I think, well, in a month's time, I need to talk to my upstream ISP and tell them that I need to increase my capacity by 10, 20, 30%. Flow size. We can look at flow size, so for traffic accounting and monitoring, for scalability purposes. But the flow size should give us a capability to monitor and route manage mice and elephant flows. If you're not familiar with the terms, elephant flows are very long-lived, large flows. So, for example, if we are to download, for argument's sake, a 10 gigabyte file, that will be an elephant flow. So that will be a very slow, very long-term download. That will keep going and going for hours and hours. Mice would be a lot of flows that will be very short in nature, but many of them in terms of numbers. So imagine the same file, the 10 gigabyte file, being downloaded as a 1 million 1 kilobyte segments. So but basically that gets broken down into 1 million pieces, each one of them 1 kilobyte, and downloaded. They've got a very different behavior because the elephant flow is just one flow. Those 1 million flows will just try to grab in all the attention or grab in all the resources and have far more of a destructive nature, if you want. So also classifying client and server generated traffic. So we can do that with flow size. Then looking at temporal traffic distribution. So aggregate traffic profiles and provide an insight into breakdown over a relatively smaller time span. So we can see if we have any problems in a very narrow time window. So for example, at I don't know, at peak time, we might see something which goes very, very wrong. Load balancing network traffic as well as conserving power utilization. So we can do that. So we can see whether we can help a bit the network planning in terms of figuring out the peak times and allocating a bit more resource, not in terms of links, just in terms of more in terms of servers, if you want, or endpoints. Spatial traffic distribution to visualize the workload on a spatial basis. So to load balance and do a monitoring network node switch, backplane utilization, and memory requirements. So to see where the traffic comes from or goes to. And also, and something that we're relatively familiar with as broadband customers, directional distribution. So to see the upload to download ratio of network traffic and client to server behavior for load balancing and monitoring network health. So we've got quite a few things to look at from a traffic profiling perspective. We also need a bit more though. So SDN requires an input to accommodate different needs. SDN will say, right, okay, so you want me to slightly prioritize, for argument's sake, voice over IP calls. Perfect, not a problem. Which are the flows of voice over IP? How do I find that out? The client won't tell me because the client establishes that quite high up. So the client establishes that at the application level layer, then it goes through TCP, it gets encrypted, goes TCP, IP, and once it's in the network, once it gets to SDN, all I can see is just an encrypted flow. There's nothing else to inform SDN because I don't want SDN to talk to my endpoints. It gets too complicated. So SDN needs to somehow figure out what's in each flow, which is not an easy task. So we also have a number of challenges. So network programmability, application input. We'll talk about network programmability later on. Sampling big bins. So we know that 6 p.m. to midnight is peak, at least in the UK. I don't know whether there are some variations in India, but I'm guessing it's the same. So once workday finishes and it's not yet nighttime, sleep time, everybody is going in front of their devices and drawing content. There's also a management overhead. So a router also needs to route. This is a phrase that I've heard quite a few years back at a conference from a speaker from Cisco. I said, well, we're happy to provide you guys with whatever statistics you want. But remember, a router is not there to provide you with statistics or to analyze traffic. A router is there to route. So let it route and do your statistics and other things separately. And also the challenges are how many features do I want to extract when I look at the traffic? So what is it the most important? And I've got concerns as well. So 20, 30 years ago, privacy was just something related to maybe toilets. Now, privacy is one of the biggest players when we talk about monitoring, when we talk about traffic, when we talk about seeing what people are doing. So it's very important. Privacy is gathering momentum, and for justifiable for justified reasons. So by all means, I'm not denying privacy. I'm an advocate of privacy, but also we need to also acknowledge the fact that the more privacy that the endpoints are getting, the less help we can provide them at the core of the network. So what did we do? Well, first of all, we looked at the features. So we're trying to, what's the task? We're trying to profile traffic. We're trying to figure out what application is inside the flow. So what features should we look at? We should look at everything that we know about the flows, from traditional accounting to timing and burstiness. We do an analysis, some sort of classification, neural network, C5, K-means, whatever your favorite is. I'm not going to be, I used to be an advocate of generic neural networks, but any sort of classification will do. And I was somehow dismissive of other classification methods because I thought they are a bit more sort of unscalable. But ultimately, it's, if your computer allows you, then go wild. Results, identify application and use it as input for an STL. So this is our ultimate aim. Okay, so how well did we do? Well, this is a quick example of this. So basically, we had a number of features, we ran an analysis, and we had some results. And I'll start, oddly enough, the other way around with the results. So these are the results. So for those of you that haven't done classification in neural networks, this, having figures on this diagonal, is good. That means that you're matching Skype for Skype. You're matching Skype control with some exceptions for Skype control, and so on. So the more we have on this first diagonal, on the second diagonal, the better we do. And as we can see, our method worked quite well. So I've got an accuracy of 94% with a 95% confidence interval. So what can we do once we've done that? Well, once we actually identified which flows belong to which applications, we can do some user profiling. And this is the bit that is actually starting to help the users. How am I helping them? Well, I'm trying to build users not as a, well, this user is only this application. A user does not equal an application. I imagine that quite a few of you are very keen, let's say, on activities like watching movies or playing games or listening to music. But by all means, you cannot say, well, yes, all my traffic is gaming. I've never watched a movie on the internet. I've never been on a web page. I've never sent an email. I've just do movies. Or no, all my traffic is emails. I've never opened a link on YouTube. I've never listened to some live radio. I've never opened a podcast. No. So ultimately, we are a combination, as typical users, we're a combination of applications, and we're not a single application. So what we did as part of the research, we put together a number of users, and we tried to figure out profiles. So we were looking at an IP address and seeing the traffic that it exchanges, identifying each of the flows in that traffic and allocating it against a category. So what kind of, if you want, applications we identify? So we identify things like emailing, storage, streaming, communications, enterprise, publishing, software, web browsing, network utility, and each one of them would actually relate to a set of activities. And you've got here, I'm really sorry about the fonts, but it's only so much that I could fit into this diagram. So, for example, if you look at profile 1, you can see that 39% is W, so that would be web browsing. So profile 1 would be users that tend to be web browsing. So they don't do much else. They do a lot, well, they do a lot of web browsing and a bit less of 20.P, which is enterprise, so corporation information system, staff portal. So this would be sort of a mixture of web searches or web browsing and corporate information. Profile 2 does a lot of C with an office communication server, if I've got it right. Yeah, I think so. I think it's C. So a lot of office communication server. Profile 3 does a lot of, again, P, a lot of enterprise, so corporation information, staff portal. Moving to H, content management system, so publishing, then over to profile 5, having a lot of G, central storage, and profile 6, having a mix of web browsing with a bit of SSS. Can't find S now, where was it? I might have a few more on the list. Apologies for that. There might be a few more further down. And having once again P for enterprise information. So basically what we're able to establish was that once we look at the applications, the user are a combination of applications, not just a single one. But do we change as users? And this is a very sort of a philosophical question. And I think that the answer instinctively would be no, not really. If today I'm doing a certain set of activities, like a bit of watching some online streaming, sending some emails, checking the news, playing an online game, that's probably what I'll be doing tomorrow as well, and the after tomorrow, and in a week's time, because my activities don't vary so much over time. I'm fairly sort of fixed into what I do as a user. So as you can see, if I look at the probability of no change, they're all very, very high. So this is just looking at a user's as a certain profile to see whether users within that profile have changed from one profile to another. So you can see that the probability of no change is in all cases above 0. What's the lowest one? 0.96. So 96%. So it's very likely that once a user is cataloged as being a part of a profile, they kind of stay with that profile. So how does this help us? Well, does this help us to tell us that it's not every day we look at it, it won't be, my God, I have to decide again. I need to reprofile them. No. The profiles are quite stable over time. So this was an analysis that ran over several months. So we know that the user that did something yesterday will do pretty much the same today. So it's a lot easier to cater for them. If we decide, right, I need to allocate this user, let's say, more priority because they don't have a lot of traffic, but they've got a lot of real time, or this user more bandwidth because they actually don't do anything live, but they download a lot, I can actually do that by knowing which applications they typically use. And we can see that graphically also over a month time. So we can see that the variation in terms of number of devices or user premises per profile hasn't changed. So that the membership varies a little bit, fluctuates a little bit, but by all means not by a great deal. So that tells us that most of the users will stay pretty much where they are along this journey. So their behavior and connectivity patterns won't change over time. Right. So we did a bit of application identification in the first instance. And when we said, right, let's try a bit better. Let's try to be a bit more accurate about it. And rather than just do a bit of guesswork in terms of volumes and so on, or in terms of IP addresses, let's try to see whether we can spot differences in their behavior. And this is very weird because bear in mind, we're talking about flows which are all encrypted. We can't see anything in them. So if we decide to look at the data, all what we'll see will be encrypted data. If we decide to look at the port, most likely we will see HTTPS. So what else can we use? We can use the inter-packet arrival time. So the time between arrival of successive packets. And if we actually plot them along a timeline, we will have bursts. How do we define a burst? Well, a burst is a train of packets that is separated by the next packet, if you want, or by the adjacent packets by a significant idle time. So for argument's sake, if you just think of your web browsing habits. So once you start web browsing, you'll open up a web browser, click on a link, look at that page for, let's say, 1, 2, 7, 20 minutes, click on another link, look at another page, click on another link, look at another page. So you can see how you'll have a burst of activity for probably a few seconds, not more than that. Then there won't be nothing happening for a number of seconds, tens of seconds, minutes, then another burst of activity, and so on, and so on, and so on. So we can identify these bursts and we can say, right, this looks a bit like web browser. But we don't know that yet, because I'm just giving an example of a typical activity. So I can't sort of say for sure if it's 2 minutes or if it's 5 minutes, that's a web activity. So, but I can see the difference. Similarly, if I was to watch a movie, the traffic for it will be coming periodically. So I won't have that many sort of gaps, because I will be constantly streaming movie as it comes onto my device. So this is the actual picture that kind of says it all in terms of application identification. So if we pick traffic that was linked to Google, Facebook, BBC, Skype, YouTube, or Yahoo Mail, we can see that their frequency varies. So if we do a cumulative distribution function of the inter-packet arrival times, they will have different shapes, very different shapes, very, very different shapes. So if we pick, for example, the Skype one, which is quite distinctively out there. Oh, sorry, no, that might be no, it is the Skype versus the BBC. So you can see that Google, Facebook, Yahoo, and BBC are quite tied together. YouTube will have a very different behavior again. So this, if we see, this is web streaming. This is this is video streaming. This is web browsing, and this would be some sort of voice or voice-related traffic potentially. They behave differently. So, given that I know that, I can try to teach a system how to differentiate them by looking at these patterns. So, I won't tell a system, well, this flow is Skype and this is YouTube. I will try, well, knowing what each flow is, I will try to see whether the algorithm can differentiate between them. So what features do I use for burstiness? Because this is essentially, sorry, to briefly go back, this is what I'm looking at. So how can I define this as a sequence, a very specific burstiness sequence? So how can I, if you want to differentiate this from a slightly different sequence of bursts? So it's one that would have the packets more closely together. And these are some of the features that we looked at. So the number of bursts, the number of data bursts, the number of packets in bursts, the number of data packets in bursts, the size of each burst, the duration of data bursts, the inter-arrival time burst. So anything that has got to do with their timing or with the amount of data that I've done in each burst. So we had a data set that was manually labeled. So we had a few hours of BBC, Facebook, Google, Skype, Yahoo Mail, and YouTube. Quite a few flows in each one of them. And then we applied them to a classifier. What was important for the classifier? So things like these, the mean and median for number of transmitted packets, mean for number of transmitted data packets, mean flow duration, max flow duration, median for first packets and the first packet, standard deviation of inter-arrival time. So I'm starting to see the burstiness in there. Also, these are traditional ones. So these are based on flows as I had before. I've got plenty of others that are the newer ones, if you want. So mean for number of data bursts, mean for the inter-arrival time data B, max for number of packets, max for data bursts. I'm not going to attempt you to be able to follow all these, but the fact that they're heavily used, quite a few of them, is important. And yes, we had a very long number of them. We had literally over 100 of them. So what does that tell us? How much information do we get as a result? Well, we're doing very well in terms of sensitivity and specificity. So if we have a look across at being able to identify the application, we can see BBC News, no problem. Facebook, some sort of an issue. Google, again, a little bit of an issue. But overall, we've got that, once again, that diagonal that indicates that the very vast majority of the applications were correctly labeled and identified. So what do we do? How does this help us. Basically, what we need to do is to figure out, okay, we know now which flows are what applications. How are we going to implement that? Who's going to benefit? Who's going to profit from that? And ultimately, we need to figure out how it will work in a if you want, bigger scenario. So we've got, if we start from here, I would say we've got the switch port monitoring that will transmit user connections to a queue calculator. So to the decision factor onto which packets to send first. And that would be all part of the traffic manager. I should mention, if you've never heard of SDN, this diagram will be a bit more difficult to understand. But the idea is that we've got essentially the traditional SDN here. So we've got the data plane and control plane, and on top of it, we've got an application plane that tells the control plane of the SDN controller how to change things. So once we get information, port information or traffic information from the SDN controller, then we can pass this as user connections to this queue calculator. We can get the traffic profile database, so we can tell which packets belong to which applications, and ultimately tell back the controller to either prioritize or deprioritize or delay or put them in a different queue, those respective packets of that respective traffic. And of course, what the controller will do, will tell the data plane to act accordingly on those flows. How will that work on a campus implementation as well? Once again, we've got the SDN controller here. So a traffic monitor would receive packets and will try to assign them against specific profiles, against specific applications and profiles. So once that is done, it's basically interacting with the open vSwitch. So SDN controller and the traffic monitor will ultimately inform the vSwitch whether to drop or enable or disable or delay traffic. So the traffic monitor will tell the SDN controller, these are the packets that need to be prioritized, these are the packets that need to be dropped, and so on. Those respective queuing tables on the open vSwitch will be affected, and the information will be updated in the traffic monitor to make sure that we've got an up-to-date image of the network. Right. So what do we do next? Well, next we can do an ISP implementation, which is a bit more complicated. And by all means, I'm not expecting ISP. So, oh yes, thank you very much. Let us have a copy, because we would like to do exactly that. But hopefully, in a not too far future, we could see deployed all over this topology some sort of centralized control. So hopefully we'll be moving at some point to an SDN controller. Why? Because it's very difficult to manage control planes individually. It's very difficult to do everything on a per device basis for two reasons. First of all, we've got a lot of devices around. And second of all, they need to communicate to actually reach a consensus. If they don't talk to each other, they might do optimization locally, but globally, the network won't be optimized. And we would end up with a rather sort of unfortunate, distributed, but uncoordinated optimization result. So if we manage to get an SDN controller that will have appropriate traffic management, that will have appropriate user traffic profiles, that will talk via OpenFlow with the respective devices all over the network, northbound to what we just implemented, southbound to the devices, and we'll be able to put in place the additional knowledge that we provide for the network onto those devices on the ground, onto routers and switches. So again, and if you want a more sort of a zoomed out version, you would have the profiling engine using some sort of processing, per user application quantification, cluster analysis module, all feeding into user profiles. All that, the profiling engine will determine will work with the traffic manager. So you will have a certain priority of each profile and application hierarchy derivation. So you'll be figuring out which user, which application must be profiled. And as a result, you'll have some root constructions that will be passed via the SDN controller over to the network plane. So you will end up with information, first of all, going from the switch monitoring over to the traffic manager. Then the traffic manager will tell the SDN controller what to do with that respective traffic. Okay, so I realized, okay, that's fine. We're doing fine for time. I've got just a couple more slides. So what do we do next as of last year, if you want? These were discussions towards the end of the project. So we're talking about multiple path TCP. You've heard a lot about load balancing, I'm sure. So you've got load balancing on servers. Also, you've got load balancing on internet. Are they not good? Well, they're both good. But if you think of load balancing on servers, the load balancing on servers is based on the CPU of the server. It doesn't know what's going out there in the network, but it says if my CPU or my memory or my hard drive are overloaded, I'll add another server. So I'm load balancing. Okay. So if the network is a bit funny, it won't be able to do anything about it. We also have the layer 3 load balancing, or whatever you want to call it, whichever way you want to look at it, the layer 2, 3, so the internet layer, if you want, in the TCP IP stack, that says, well, if a path is congested, we'll load balance and we'll send packets on separate paths. So both of these work, but neither of them considers what traffic looks like. And traffic ultimately looks like a series of TCP flows. And what TCP flows they like about themselves is they want to stay together. So what I would like is one TCP flow on this path, one TCP flow on that path, and I can't split that. If I have, for example, an elephant flow, I can't say, well, half of the packets go that way and the other half the other way, but on 2 different flows. So I can use the multipath TCP, which essentially opens or provides a layer 4 load balancing. So it's open more connections to be able to stream some of the information, or to send some of the information on different connections, if you want. Okay, we also need to deal with security. I mean, we've got information leakage and network attack detection through the traffic footprint. If we go back a bit in time, the networks were beautiful. They were quite beautiful in a medieval way. So it was just this very big high fortress with walls around and a very small hole, which was the firewall, that information was going in and out. By information, I mean everything. Everything was inside and going only via that connection to the outside world. So that was a very well-designed, well-protected concept of network or information. Now we've got the equivalent of it for current days is more like Swiss cheese. You know, the Swiss cheese, the one with lots of holes in it. This is pretty much what a typical corporate network looks at the moment. Why? Because I've got things like these. Oh, you can't see it. Sorry. In a better world, you'd be able to see it, but I think it's blocking my. Oh, I'll try again. Let's see now. You can probably just about see a mobile screen. Yes, you do. So I've got mobiles. And the mobiles, I want to connect that to the network. Why? Because I do some of the work on my mobile. But the mobile isn't restricted by my corporate network. And that's how the Swiss cheese starts to come in. And I've got my laptop that I do some of the work. From where? From home. What do? I VPN. What do I end up when I VPN? I'm inside the network, but with a device that might be from outside the network. And there are lots of examples like this. So I end up with something that is very uncontrollable, but I need to keep an eye on all this traffic. Ultimately, we need to look at TCP connections individually and to try to analyze as much as possible about them. And we need to, in terms of security, there's something very interesting about it. So, you know of you might have heard of the concept of network scanning, where you, let's say, ping or try to open a connection to a certain port to see whether that computer is available or whether that port is open on that computer. And that is very easy to identify. So basically, you've got the most basic firewalls would have a trigger. If the same IP address initiates multiple connections to a single IP address or to group IP addresses, which are higher than a certain threshold. So let's say if an outside IP address is trying to open more than 50 connections per second to my network, I'll block it. But how much? I don't know, a minute, an hour, a day, a year, a decade, up to me. So I can identify that and block it. And how do I know that? Well, basically, I need to keep all the traffic in the last second and see whether there's been any external IP address that did 50 connections. So that works. Slow scan, however, says, no, I'm not going to send it as fast as possible. I'm going to try to open one port per 10 seconds. And I'm not going to see it anymore. That won't be visible. So that'd be basically under the radar attacks. Whatever measures I've got in place, I need a very, very long timeline. So, oh, that IP address trying to connect to multiple ports in my network over the space of 1 week. I can't store all that information. It's because I haven't got the resources. So slow scans are notoriously difficult to identify. Fairness, we need to talk about heterogeneity. And it's quite hard to pronounce it, but it's quite important to discuss. So for those of you, I think that I'm guessing that the majority of my audience is quite young. But for those of you that might have seen them a long time ago, we used to have QSIF. So QSIF in terms of size is something about this big. It's the old phones that used to have, I think it's about 230 by 144 pixels. It's slightly bigger than a stamp. QSIF was amazing. 20 years ago, this was video. You could actually watch a video on a phone. It didn't quite look like a video. It didn't have the right resolution, but you could see something moving there. Then we had 3G. Then we had 4K. Then we had 5G, 4G, 5G, and so on. So how do you ensure fairness in a network that has got all this range of connections, from users connecting to a stamp-like video mobile to users that's not, well, I've got a tablet which requires sort of 4K input and I need 5G network. It's unfair to connect, so, well, each one of them, you'll get 50-50 traffic. No, there's no point. The first user won't be able to download more than 2 kilobytes per second. And the second user, if you actually restrict them to anything but sort of 10-20 megabits per second, they'll have a very poor user experience. Also, we need to be fair between video and web browsing. So how do we ensure that they're both running comfortably, I suppose? So some users will require web browsing, some users will require video. How do I make sure they're both, they get similar treatment or fair treatment? Also, I mentioned earlier on about elephants and mice. How do I deal with them as well? So there are a lot of discussions about fairness that still go on. So these are discussions that I posed with my students last year. Some of them are quite sort of proudly standing at the moment. Clearly, quality of service does not exist anymore. Nobody cares about how well or how bad the network is. Everybody's wondering how happy or how satisfied with the service the user is. So quality of service gone, long live quality of experience. So long live the opinion of the users and how the user's perception of the application is. What next? I've updated it for this year because we're finally seeing SDN transitioning from that theoretical concept to practice. What do I mean by it? I think that the whole slide revolves around this Tofino barefoot switches, which are just one example. Basically, we're talking about programmable hardware, and programmable hardware beyond what programmable means for a computer. Programmable hardware that will be able to run very fast operations in with a very pre-specified or preset set of instructions. So there's been a lot of discussion that SDN cannot be faster than traditional networking. I suppose that still stands. So yes, I'm sure they cannot be faster, but it can definitely be smarter. And by being smarter, it could be faster as well. So what do I mean by that? It will not be able to sort of commute change per packet any quicker than it's doing with a traditional networking, but it can take more intelligent decisions. So for example, if I send traffic, which is a combination of bulk and video streaming and voice over IP, it would be able, by analyzing the flows, to prioritize first the voice over IP then the video, then leave the bulk at the end, probably not even prioritize it. This is something that the traditional networking couldn't do on the fly. So we'll need to have some cross-layer programming to actually be informed by the application about the nature of the flow. Also, essentially what we're seeing with SDN is a load balancing between the data plane and control plane. I did have that quote earlier on about the routers must be left to route. And this is exactly the point of it. The fact that the data plane will remain with the handling of packets, but the control plane, which can be externalized, will be dealing with a heavy thinking, I suppose, with trying to figure out what's happening in packets and what's happening in flows. And P4 remains, it's a programming language, feel free to look at it. It's for programming ASICs and programming devices that are network programmable devices, let's put it this way. Why is that? Because the terabit is the new gigabit. So we're talking in awe. So if we go back 10, 20 years ago, gigabit, wow, that's so fast. That you need a lot of resource for that. All of a sudden, 10 gigabits started pushing in, 100 gigabits started pushing in. By now, terabit is becoming almost the norm for large volumes of data. So terabit wouldn't be something that you only see in terms of sort of, let's say, I don't know, UK communicating to another country. It could be just within the space of a few data centers talking to each other. What does that mean? Well, that means that nothing can be delayed. I cannot say, what you just store the traffic there and I'll have a look at it later on. No, later on will mean sort of a 1 hard drive per minute if you want to store that information. So you'd need to process and interpret traffic at terabits per second as if it was sitting on a trace to be processed when possible. And there's been some wonderful research being done beyond the realms of our center to actually look at how we can pack as much as possible analysis, as much as possible processing in the control plane, so that we let the data plane do its thing while we do the clever bit, the thinking bit, as part of the control plane externally by devices able to handle that. And almost in time, that's the end of my presentation. Thank you very much. Any questions?
Yeah. Thank you very much, Professor. It was really a wonderful talk. Now the floor is open for discussion. Please go ahead and ask your questions. Yeah.
Good evening, Professor. Thank you for the detailed and fabulous presentation today. We are really happy with us today. I have some clarification on this SDN itself, because this SDN is going to accommodate more amount of video traffic. So if any of the network which is accommodating more amount of bandwidth is concerned, there is a possibility of control over it is going to be the bottleneck for this type of networks. So how this SDN will take care of the control overhead while handling the large amount of traffic?
Okay, I think I understand where you're aiming with the question. So as I mentioned earlier on, if you give a network 1 gigabit per second, whether you give it SDN, traditional networking, whatever, it won't go beyond 1 gigabit per second. It's not, and we know that, and the ISPs know that, everybody knows that. However, we can decide how to slice, how to separate that 1 gigabit per second. If I'm doing video, essentially, if the network is under some sort of strain, so if the network has got some sort of congestion, everybody must have a share of that congestion. So if you think of an operating curve, I'm not talking about here. I'm not talking about here. I'm talking about that sort of intermediate part where the network is not completely killed and not completely empty. So as congestion starts to build up, we need to more cleverly allocate bandwidth to each flow. Traditional networking can do 3 things. One of them is nothing, and that's quite straightforward. The other one is trying to sort of follow up some information that is being given. So either inserve or diffserve, so listens to some advice from above and put that in place. And the third one is giving each flow, each user, each IP address, each something, a fair, equal share. None of these three is particularly appealing. So if you do nothing, it's probably the worst case scenario. If you require some additional signaling, that becomes impossible, unmanageable in the current internet. And if you give everyone the same amount of traffic, ultimately you will punish the ones that might need more traffic. And ultimately it will be almost sort of unfair for everyone. So let's say if I sort of, I don't know, if you're, just to take an example, I like to drink a lot of water. So if I was to drink 2 liters of water a day, and then somebody else would drink, let's say, half a liter of water a day, the fair thing would be to give both of us 1 liter a day. So, well, how that's going to help? I'm going to be thirsty, and that person will actually throw away some of the water. So it's not going to help either of us. So in that, from that perspective, SDN will hopefully have a more intelligent approach in managing these flows and giving each user, I wouldn't say as much as they want, as much as the network can give when it's under strain, when the resources are limited. Does that answer your question a bit?
Thank you, Professor. Thank you for the detailed information.
Thank you.
I have one more
Please.
clarification also. Since the network, in that case, everywhere the memory requirement is going to be a biggest issue, no? So SDN, is it having any minimum requirement of the memory in every router or something like that in SDN part?
I understand that the challenge is to actually do this as intelligently as possible. I've seen quite a few papers this year that essentially work out what needs to be calculated and do it as fast as possible. So if you, let's take the example of a slow scan. If you're able to map onto a table all the connections that happened over the last day, month, whatever it is, you won't need to keep all the traffic. You'll just need to keep a record of each connection. So instead of doing, if you're familiar with networking, doing a TCP dump of all the traffic, you just do a net flow of all the traffic. So for each flow, we'll just record source IP, source port, destination IP, destination port. So you'll just reduce the amount of information that is saved for each for traffic. So what's now become known as sketching. So you're not actually keeping all the detail. You're throwing away quite a bit of it, and you're keeping only the essential. So the memory, by all means, will be dependent. So the amount of memory you have will actually dictate how much analysis you can do. But in the papers that I've read, what tends to be the bottleneck is the processing, the actual speed of the CPU and the ability of the machine, the ability of the hardware to deal with terabit per second, essentially, data, and being able to calculate that in real time. And that's where the load balancing comes in place. And I've seen some very interesting research onto load balancing processing rather than load balancing traffic. So you'd actually get the packets recorded by a unit, and then traffic or information will be redirected to other units for calculating the respective information and feeding them back to a database.
Okay, thank you.
Thank you, Professor.
Like any other questions?
Professor, yeah, Professor, this is Sujata here. I have
Hiya.
one question. I have a question regarding the internet packet arrival that you have shown a graph over it. It's like where you have a burst of data, and you have shown a graph for data of Google, Skype, and etc. And how do we have a God band between the packet burst of data when for data collection of Google or Skype or any data collections in the frames of data arrival? Do we use God bands between the burst of data? Do we use because it may have lead to collusion or packet identification? We need to use God band.
Sorry, God bands? Don't know what you mean by that.
God band instance. So when we start between the packet to identify each frame, each new packet, separating each packet, we may use some unutilized band, which may identify the next packet. Between the packets, do we use some unutilized bands in order to prevent collusion or collision of data or overlapping of data? Do we use some unutilized band between the packets?
I think I understand the question. Are you referring to some sort of scheduling? So if we have some gaps, we can insert more packets in between the gaps. Is that what you mean?
Yeah, that's what. But
right.
It's a free band that can be so that each packet can be to avoid collusion or overlapping of data. So do we use some unutilized band between the frames of data?
I understand. So I think what you're referring to is a more media access control issue to do in the local network, in the access network. Is that correct?
Yes, sir. Yes, sir.
Yes. So we haven't explored that at all. I can say that certainly we haven't explored that. We only looked at what happens when you aggregate. So aggregation and beyond core. So we didn't look at the burstiness in the local network. We just looked at what happens, or how can we identify the connection, the application based on this burstiness, and being able to apply a filter, a policy, a control mechanism on it afterwards. But no, we haven't explored that. You're right. We haven't explored the opportunity of time multiplexing, I suppose, to actually reduce congestion in the local network. It's quite hard because the applications don't like to be told what to do. So you can technically have a queue in there to wait for the packets to be sent. But what tends to happen is that the congestion is not in the access segment. That the access segment tends to be over provisioned. It tends to be towards aggregation and core, where you've got contention, gathering, and having not enough bandwidth for how many clients are there.
Fine. Thank you, Professor. I have one more question that regarding the queuing table that we make it. Is the algorithm used for the queuing table is the same for any type of data you collect? Either it's going from Skype or any other. It's algorithm is the same for queuing table that you make it. Is going. The algorithm is being same for utilized for all the type of data, or it is different?
I understand the question. Again, you have very good questions, but you're actually aiming at sort of our segment was a bit higher up towards layer 7, rather lower down towards scheduling. So the point that we were trying to put in place with the queue was the fact that essentially applications will be put in queues according to their predetermined priorities. So from our perspective, we had no interest, no control, no decision of the queues. We just said, if you have a video queue, we know which traffic should be put in there. If you have a web browsing queue, we know which traffic we should put in there. Afterwards, what you do with these queues or how you want to schedule traffic is your problem, I suppose. What we did was to identify it and to feed it to the right queue. So you take the best decision, which is, I'm guessing, is where your research will come in, and we'll say, right, no, don't worry, I know what to do. You just tell me which one it is, and I'll do the right scheduling for it.
Actually, it has been done as if you say, Professor, it's like a procedure that is being done for everything. So it has not been discovered for congestion or what type of algorithm. It's not, it's a set of procedure that you've been profiling that data. That's what I understood. Thank you.
Yes.
Thank you, Professor.
Thank you very much. Thank you.
Thank you. Is there any other question? Anybody wants to ask? Okay. Okay. Thank you, Dr. Bogdan. It was really a wonderful talk, and I can see a lot of interesting questions coming up from faculties and students. So there is a lot of potential to do joint collaborative research as well. So maybe
I look forward to the follow-up discussions after this. I'm happy to stay in touch. Thank you, Deepak, and thank you to the audience as well.
Thank you. Thank you very much. Good day to you. Take care.
Thank you very much. Bye-bye.
Bye. Bye. Bye.